some of the columns were completely removed, and in one case, an entire frame was removed. And the bottom left is the baseline without kernel, and you could see that when the frame goes blank, without side info, kernel cannot actually do anything about it. Whereas with kernel, it could make some sense out of it, not total sense, but a little bit more sense. So in conclusion, we presented an approach to incorporate different dimensions to a standard matrix completion problem by transforming it to a tensor completion problem. We also proposed a way to incorporate more side information such as the social network of users, the product attributes, to further enhance this approach. And we tested our tensor completion approach for 2 tasks. One was video restoration and the other was recommender systems. And though we were not able to show significant improvement in the overall case, but we were able to show significant improvement for the challenge, for the cold start problem challenge. And yeah. Thank you.
Questions?
So how does having the kernel affect the time complexity of the algorithm?
We did use some heuristics to decrease the, so yes, computing the kernel does take a lot of time. However, and taking inverse of it would take a lot of time because most of it is a dense matrix, but we did do some heuristics, like we only computed, for inverse of kernel, we did not do it over the entire dense matrix, but only for the top 20 similar items or top 20 similar users. And then,
Other questions? How does your performance on the video compare to like current state of the art in video restoration?
So okay, we haven't actually compared it with the state of the art yet. We just did that.
So I'm not convinced that just tensor completion will work well, but I mean it seems to work better than
Yes.
yeah, another thing is that we currently haven't used any kernel for video completion problem. We haven't used any kernel which is derived from the features of the images, from the image recognition literature. So probably if we could use that domain knowledge to create that kernel, probably it will do much better. Not sure, still not sure.
So what was the largest data set you were able to?
I think opinions is around 200,000 items and 60,000 users.
All right, thanks. Let's go like the forms.
I think so, right?
When did you know it? Probably about 9:40 or so. Or do you want to choose Okay. Yeah, I'll use yours. Yours has the PDF on it. Oh, these are the assignments. There's Is this the microphone? Okay, I guess I'll be looking back like, is this working? We're good? Okay. Hi everyone, I'm Neil, and this is YJ and Marwan, and we're going to be talking about our project Sparse and Diverse Factor Models via Determinantal Point Processes. So I'll begin by giving an example and some background on factor models and determinantal point processes. Then Marwan will walk us through the model and the inference, and YJ will talk about our experiments. So seeing as Thanksgiving just happened, I thought it would be fun to do a Thanksgiving example to kind of motivate factor models. So suppose we have a big table full of Thanksgiving homemade pies, and we have the nutritional information for every single one of the pies. So big long vectors of how much fat, protein, etc. And our goal is we don't know what ingredients go into these pies or how much of each ingredient goes into which. So we kind of want to do cupboard learning, where we're trying to learn everything that's in the cupboard to make pies, as well as how much of each ingredient goes in these pies. So we could view this idea of learning the nutrition facts as nutrition facts are a linear combination of the nutrition associated with each ingredient, plus a little bit of error just for noise. So we could view this as like in matrix form, as each x corresponds to a particular pie, each lambda corresponds to a particular ingredient and the nutritional information with it, each eta is the is the quantity of each ingredient in each pie, and then we've got some error. So this is a factor model, where x's are our observations, the lambdas are our factors, the etas are our loadings, and then epsilons are our errors. Our goal is to learn both lambda and eta, so both the ingredients and the quantities. So we can represent this quite succinctly in this sort of matrix expression. So in our particular application, we're interested in getting a few desirable properties out of a latent factor model. We want to get sparsity, which is the same as kind of having a short recipe. These are homemade pies, so compared to everything in the cupboard, we don't want to be using every single thing we have in every single pie. We want to use a small subset of the ingredients for any individual pie. We want to get low error, which is a little bit self-explanatory. And then both low error and sparsity have been achieved before, but we also want factor diversity, in that we want to use the ingredients included in each pie. We want to use prior information that we know the ingredients should be diverse. We're not going to use 3 different butter substitutes